Okay. Does anybody have any homework questions? I knew that's going to happen. It's like I'm Charlie Brown with a football. um, okay. So hopefully at least a number of you have started it. Okay. Yeah, oh yeah, yeah. I kind of figured it in your case. Okay. Well, you still have a whopping.
Excuse me. I think I did have one, but it was on the exploration 3.17.
Yeah.
It has the zero in the diagonal. So should we switch that row with the first? Or does it matter about which row we switch with?
Okay. 1.10.
Yes. So 94, page 94. Yes. I have it.
Okay. Wait. So you're talking about the zero in the.
Right. So should we? I mean, does it matter about the zero being there?
One in the first row, you mean?
No, in the last row.
No.
Okay. So just.
Yeah. So this matrix is contrived so that pivoting is not required. Yeah. But there's not going to be a division by zero situation.
So we can just leave it as is and then still carry out the pivot decomposition.
Yes.
Okay.
Yeah. And what will happen is, I always found it when I would do an example of Gaussian elimination on the board that I would do something like, of course, my matrices would all have integer entries, like this one, and then I would maybe set the 1, 1 entry to 1, so that the numbers would work out nicely. The numbers are not going to work out nicely for this, because computers don't care. And you're acting like a computer for this problem. So you can't, so you don't get a lecture either. Okay. All right, yeah, so that zero is not going to present a problem. Any other? Okay. I was hoping one question would open up a floodgates, but that's just my naivete again. So, okay, well, I guess we'll see how you all are doing with that on Monday. Okay. So I just have this one subsection to get through. It may not fill the whole time because I want to allow time for questions. Silly me. But if it doesn't fill the whole time, I'm sure that no one's going to mind. Okay. But at least I can cover it thoroughly. Now, so to recap, with the least squares problem, so this is a terrible piece of chalk. Who dares bring that into this room? Ooh, I do not. This is. Where does crap come from? And you can tell just by picking it up. It just feels wrong. So. Okay, I'm gonna get some good chalk. So, A is a M by N matrix, assuming that the rows is greater than the number of columns, and that the rank of A is N. So all the columns that we have are linearly independent. And is to, so our goal is to minimize the 2 norm of b minus ax for a situation where we're not able to find x if ax equals b. We're just going to try to make this residual r as small as we can in the 2 norm sense. And so the approaches that I derived last time normal equations. So you solve A transpose A x is equal to A transpose B, so you can fall back on the chapter 3 material, use it like a Cholesky factorization. But the condition number can be quite large because you're squaring the condition number of the original problem. So that's a reason not to use that approach. So the approach I'm going to focus on in this class and beyond is QR factorization. So we factor A is equal to QR, where Q is an orthogonal matrix, and then R has this kind of setup, where the first R is the same size as A, but now the upper part of it here is upper triangular. So in that case, to get the actual solution, x, then we're solving a upper triangle, wait, that should be R1. We're solving this upper triangular system where Q has this breakdown. So we have m rows, n columns, m minus n columns. So taking the first n, multiplying a transpose with b gives the right-hand side of the system, and then we can solve this upper triangular system using back substitution, and then we're done. Okay. So this approach has the advantage that we don't have the terrible conditioning. So this approach, so we're not trying to solve a problem that is so sensitive to changes in data as we would be in this case. But the QR factorization is still pretty dang expensive to compute. So so I can spend the next few classes talking about different approaches to that. Okay. Now, actually, so really, another way of describing how we get x here is if we have a QR factorization, then we can compute Q transpose B. And that lets C equal the first n components of Q transpose B. Now, put another way, this is often how we describe these things. We're taking whatever matrices or vectors we have and breaking them down into pieces if we only need a piece of it. So this is a vector of length m, where m is greater than n. So we're taking the first n pieces, and that's our C. And that's the right-hand side of our system, which is equivalent to the Q1 transpose B I have there. And the result of that is the 2 norm of B minus AX turns out to be equal to the 2 norm of this, the rest of a vector, D, which is also equal to Q2 transpose B. So these remaining columns. So it gives an idea of how close we have come to solving AX equals B exactly. Okay. So how do we actually get this factorization? Whoops. Sorry to whoever was watching at home. So sorry, Teresa. All right, so 3 approaches are Givens rotations, which is what I'll talk about today, then householder reflections, which will be for Monday, along with homework questions, right? I know, silly me. And then last approach is I can't spell anymore. Graham-Schmidt orthogonalization. And it turns out that all of these approaches, all 3 of them, are useful beyond this setting of trying to compute the QR factorization. When we go to compute eigenvalues, both Givens and householder transformations will be helpful. Graham-Schmidt orthogonalization can be used for orthogonalizing any kind of vectors. Here we're just talking about vectors in Rm, but for example, constructing sets of orthogonal functions like orthogonal polynomials. Graham-Schmidt is useful for that. So, and that's what happens. Really, one of the points of this class is to acquaint you with tools or techniques that could be used beyond the particular problems that we're studying. Okay, so now we'll take a look at what are Givens rotations and how we can use them to reduce a matrix A to upper triangular form. Now, when I put it that way, it seems kind of redundant because you already have a way of taking a general matrix and reducing it to upper triangular form. And that way is what? Yes, I heard someone whisper it. Okay. Oh, that's okay. Gaussian elimination. But the thing is, when I was deriving QR factorization approach last time, I started with this, and I put in a matrix Q transpose, and I used that to reduce A to upper triangular form. It's like, well, why can't we just use a row operations from Gaussian elimination? And the reason why is, if we're going to transform this vector here, B minus AX, we have to do it in a way that preserves its length, because we're trying to minimize its length. And if you multiply a vector by an orthogonal matrix, as I proved last time, that preserves the length. Whereas if I start applying row operations to this vector, that would have the effect of reducing A to upper triangular form. It would not preserve the length. So whatever solution X I computed as a result of that process, it most likely would not minimize b minus ax. So, so these transformations that you're going to see are somewhat similar in nature to what you do with row operations in Gaussian elimination. We are literally going to be doing row operations on A. The difference is, because we have to come up with an orthogonal matrix, Q, we need orthogonal transformations. That's the key difference. And the nice thing is, if we have a sequence of orthogonal transformations, and we multiply them all together, that product is also orthogonal. So that's how we're going to get this Q here. We're going to break the process down into individual orthogonal transformations, and their cumulative effect will be multiplying by an orthogonal matrix. Okay. All right. Now, that's right. The glare zone. It always seems to move. It's like a monster. Okay. No, that's not good. That's close as I'm going to get. Now, the funny thing about Gibbons rotations is they were not invented by Gibbons. Mathematicians are really bad at naming things after the right person. They're actually invented by Jacobi. Maybe they felt Jacobi had enough things named after him already, I don't know. And for a different problem, an eigenvalue problem, where these exact same things are used, in that setting, they are called Jacobi rotations. But maybe Gibbons, I don't remember, but Gibbons may have used them for this purpose, and that's how his name got attached to him. I don't know. But yeah, he needs to do better. Probably not bother to have anything named after myself because someone screwed up anyway. Okay. Now, so we're going to start with a very simple problem. Given, that was an unfortunate choice of word, but anyway. I've done worse. Just a 2 by 2 matrix A. By an orthogonal matrix Q of this form. C minus S, SC. I want to make sure I have the right notation here. Yes. Where C is cosine of some angle, and S is sine of the same angle, such that Q transpose A is reduced to upper triangular form. In other words, there's a 0 down here, and I don't really care what's in these other entries. Okay, I just want to make that entry 0. So, in other words, I'm computing a QR factorization for a 2 by 2 matrix. And then I'll be able to use that to carry it out for a general matrix. Okay, now, first thing is, why is it that I'm using this form for Q, using these sines and cosines? Well, it turns out that you can express most orthogonal matrices. Well, actually, I hesitate to say all of them, but I have to be careful about that because this is going to be a general rotation matrix. An orthogonal matrix can also be a reflection. So actually, Yeah, so it doesn't cover all orthogonal matrices, but just about. And you can confirm that by computing Q transpose Q. So if I take Q transpose Q, so Q transpose, I move a minus down here. So C S minus SC, and then Q. Okay, so we go ahead and carry out the multiplication, like C squared plus S squared. And then we have minus CS plus CS, so that's 0. And then minus CS plus CS, again 0. And then minus S, and then C and C. So we again get C squared plus S squared. But the only trig identity that everybody remembers, cosine squared plus sine squared equals 1. Yeah, so this is the identity matrix. Okay, so this is indeed an orthogonal matrix. Okay, now, just to see how on the ball you are today. If you know that Q transpose Q is identity, and I'm going to assume that Q is a square matrix. Okay. How do you know, without actually going through trouble computing it, that that is also true? What? Yes, it has to do with the inverse. Because this is saying that Q transpose is the same as Q inverse. But the inverse of a matrix is, well, yeah, in either order. Yeah, the inverse is unique. So yeah, but yeah, you can multiply in either order and get identity. But I had to say that they're square because if Q is, say, n by k, where k is less than n, you can have Q transpose Q equal to the k by k identity, but Q transpose is not the n by n identity. So the assumption that Q is square is essential. What happens here, and we'll see, we might see this later on, this is an example of what's called a projection matrix. It projects vectors into a space spanned by the columns of Q, which is not the whole space, because k is less than n. All right, so I'm bringing this up because of this common mistakes that students make, like assuming that if you have this, you automatically have this, but you only do if Q is square. And why little things like the uniqueness of the inverse are important. Okay, so this 2 by 2 matrix Q that we have, we see that it's an orthogonal matrix. So Q transpose A. We'll just write out what the product is. Okay, so we have C S minus SC. Also, it may seem strange that I wanted to work with a transpose, but I promise you that will become logical in the end. Times A now, I only care about this entry down here, the 2, 1 entry. So I'll just write out what that is. So we're not going to touch the second column of A at all. So I have minus S A11 plus C A21. And then who cares what we have up here? And I want this to equal 0. Okay. So that means I need SA11 to be equal to CA21. And then what I'll do is square both sides. And then I'll use everyone's favorite trig identity to get rid of the s squared, because that's a sine of an angle. So s squared is 1 minus c squared. So now I have an equation characterizing at least the cosine squared. So now I just need to solve for this. So if I distribute, so doing something that your 101 students can do, but being overly optimistic. Okay. All right. And then I want to gather all the c squared terms on the right. So now I have a1 squared is c squared, a11 squared plus a21 squared. So now I can solve for c. So c is plus or minus a11 over square root of this. All right, so now, so I can choose either one. Just for convenience, I'm going to choose the plus sign. But I mean, C could still turn out to be positive or negative depending on whatever A11 is. But just to reduce clutter in the formula. So now I have a cosine of my angle. So A11 over square root of A11 squared plus A21 squared. Okay. Well, now I need the sine of my angle. Well, the square of that would be 1 minus c squared. So that would be 1 minus, so I had c squared down here. 1 squared over. So if I do the whole, again, things your 101 students ought to be able to do, but probably can't. Common denominator, all that good stuff. What you'll end up with is a 2-1 squared. So the other entry up top. So again, you take a square root and you get a plus or minus. So again, I'll choose a plus sign. Choose positive square root. So S is a 2-1. So now we have our C and our S, and so that determines our Gibbons rotation completely. So, sure enough, I have minus SA11 plus CA21. I write this on full. So S is, I have a minus up front. Times A11 plus cosine, so the A11. Oh, sorry again, Teresa. denominator is just watching this. A21 squared times A21. Well, the denominator is the same in both cases, and you have minus A11, A21, and then you have plus A11, A21. So as hoped for, you get 0. So this is indeed a orthogonal matrix that, when multiplied by A, gives you something that's upper triangular. Okay, so any questions about how C and S came about? Now, we can say something more, that if we look at how, not just that one element, but the whole first column turns out. So we have CS minus SC times A11, A21. So we already know that the second entry, as planned, turns out to be 0. So given this C and this S, what's the first entry turn out to be? So, I mean, it'll be CA11 plus SA21. But if we try to simplify that as much as we can, what are we going to get? Try to work it on paper if you like.
Square root of A11 squared plus A21 squared.
Yes. Okay. Now, one way to see that without carrying out the multiplication is that we're multiplying this vector, this column of A, by an orthogonal matrix. When you multiply a vector by an orthogonal matrix, it preserves length. Well, for this vector to have the same length as this one, this component's 0, so all the length has to go into here. The only thing you couldn't tell up front is it plus or minus. Because we chose the plus signs for both S and C, it turned out to be plus. So then you can see that the new vector has the same magnitude as the old, it's just one of the entries is 0. Okay. All right. Now, I'm calling this a given rotation, and so in general, multiplying by Q or Q transpose does in fact rotate a vector. So Q transpose times whatever vector xy actually, I'll make sure I get this right. Okay. Rotates the vector xy counterclockwise by an angle of by the angle theta. Okay. Whereas let's see. Something seems off here. Wait, Q is C versus SC. Okay. If I found a mistake in the book, that's going to piss me off. Because I already found one mistake today. Well, a student found a mistake. Okay. 0. And let's suppose that theta is equal to a simple angle like pi over 2. So what we get, taking the first column of Q transpose, is C minus S. So like cosine of pi over 2, of course, is 0. And that's minus 1. So, dang it, it looks like I did mess it up. Compared to what is in the book. Oh, no? Okay. Sorry. The book was correct. What I wrote here is wrong. All right. Rotates clockwise for the angle theta. For some reason, when I was looking at the page in the book, it was like, I thought it was referred to Q and not Q transpose. And that's how you can tell, because this is what I would do to keep it straight. Here's the vector 1, 0. I rotate it, and I get the vector 0, minus 1. Well, that would happen through a clockwise rotation by 90 degrees or pi over 2 radians. So Q transpose rotates clockwise, whereas Q rotates counterclockwise because it's the inverse. It's going to undo that rotation. All right, so at least it's not a second mistake in the book. Okay. All right. So now what we can do is anytime we want to zero an entry of a 2 vector, using an orthogonal transformation, we know how to do it. We can get the cosine and sine directly from the entries we're working with. And the thing is, if we're trying to zero, for instance, certain entries of a column, we can just keep picking pairs of entries and zeroing out as we go. And I'm going to show you in a little bit how we use a sequence of rotations like these to reduce a matrix to upper triangular form and get our QR factorization. But before I do that, there's one sticky point I have to address, because mathematically all this is fine and dandy, but you have to remember that it's a computer that's going to be doing all the work here, and that introduces a complication. Oh, I shouldn't have done that. So, all right, so for a general case, so for general vector AB, the R0 or R is square root of A squared plus B squared, and we get C is equal to A over square root of A squared plus B squared. S is equal to P over square root of A squared plus B squared. So that's how a general 2x2 Gibbons rotation works. But we have to take issues of computer arithmetic into account. And I'm actually going to give you equivalent but different modified formulas for C and S. Let's see how far we are into class. Okay. Now, so the problem is, what if A or B is extremely large? So large that computing A squared or b squared causes overflow. In other words, a number that is too large to represent in your floating point number system. Because in any floating point number system, you can only represent numbers with a limited range of magnitudes. Now that range is pretty generous, like in the typical IEEE double precision floating point system that most computers use. You can represent numbers like around 10 to the 308 power or something like that. So chances are you're covered. But we have to be prepared for this possibility. And it actually gave us a horror problem in that 460 that hardly anyone got, no matter how many hints I put out there. It's kind of aggravating. So what do you do? So if A is larger than B, then what we do is I'll write out what C would be. It is, I can factor out an A squared and then pull it outside the radical and get absolute value. And what I'm left with is 1 plus B over A squared. So then what happens is A over the absolute value of A is just going to be the sign of A. So 1 if it's positive, minus 1 if it's negative. So that's how I could handle C. Now, as for S, if I use a similar approach, I'm going to have the same denominator there, and I'm going to get B over the absolute value of A. I have 1 plus B over A squared. Okay, so what I could do is, from that, I can give a more practical procedure that doesn't have this floating point issue. Okay, now, whoops, sorry, okay. Of the formulas I have here are going to assume that one thing or the other is positive. Okay. Yeah, I'm not liking that. Okay. Well, that could be something for a book to address. But so what I can do is I can let T equal B over A. So that means that actually, no, I can do this on a fresh board. So if I let T equal B over A, then my cosine would be the sine of A over square root of 1 plus T squared. So the nice thing is, because we're assuming that A is larger than B, the number we're squaring is guaranteed to be less than 1 in magnitude. So we have no possibility of overflow issue. Because it's a squaring that's the problem. So the square root of a squared plus b squared, the final result might be okay in terms of magnitude, even if a is very large. But because we're computing a squared in a process that's much larger, that's why we might have a problem. So, and then what we can do is S, if I compute C times T, so that would be B over A sine of A over square root of 1 plus T squared. I think I need a sine of A for that also. Okay. Okay, so A squared plus B squared. Oh, actually, no, I don't. Because A divided by sine of A would be its absolute value, which gives you the original formula. Okay. So, yeah, in the book, the sine part is missing, so it's something I'll have to deal with. But yeah, because it's important that the sine of C and S are consistent with one another to make sure that the proper entry is zeroed. So, dang it. Today is find mistakes in the book day. Okay. Oh. Those dang IVN classes. Okay. Yeah. So there's something to fix in the book because I just looked it up elsewhere. That sign thing is supposed to be there. Okay. And then if the that's for a case where what is it greater or equal to doesn't really matter. And if it goes the other way, or B is a larger, then you just flip things around. So T is A over B, and your sine is the so use T for the opposite purpose now. Okay. And then C is equal to S times T. So if you were coding this up in MATLAB, then this is how it would work. Okay. Now, that's interesting. Like in Galb and Van Loan, a different approach is given where, oh, but they use different signing conventions. Okay, so it's just not really equivalent. Okay, good to know. All right, but let's hear agrees with a Wikipedia page. So, because Wikipedia is the authority, everything is right. Okay. Okay. Although if B, okay. What's interesting though is all of this affects not just whether it zeros correctly, but also whether this other entry here, which is going to be plus or minus the magnitude, depending on what signing conventions you use for this, you may get minus the magnitude. Okay. All right. Okay. So, because then what happens in this case is, so if I go down here, A times cosine plus B times sine would be equal to A sine of A plus B sine of A. Let's see. A B squared over. Okay, and then if I multiply top bottom by A, okay, and then A over sine A is the absolute value of A. Okay, so this is going to be R with a plus sign. Okay. Okay, so yeah, so whereas Galvin and Lone has something different where they actually choose the minus sign for the sign, just no matter what, which I find really puzzling. So then what happens is, yeah, we still claim we're going to get minus R, so or positive R, so okay. Well, I don't want to spend any more time on that. Okay. But the point is, you have to be careful to avoid overflow, and by making sure that you square whatever you're going to square is less than 1 in magnitude, but checking. So it does involve an overhead of an if statement, checking whether A or B is a larger of a 2. But you can guarantee not having that problem. All right, so now, as for how to use this in a to obtain a QR factorization. Okay. Okay. So let's suppose I make a rectangular matrix A, more rows and columns, like we're assuming for a least squares problem. So in this example, 5 by 3. Okay. So the idea is let this matrix Gij say transpose, be a given row rotation. Rows I and J. So I'm going to multiply A in the left by these rotations to zero out a specific entry. So what's going to happen is, in this case, I need to zero out, to make this upper triangular, all of those entries that I boxed in. So now there are many ways I can do this as far as like the order of transformations, but I'm going to pick a systematic ordering here where I'm going to go from left to right, like working on this column, this column, this column, just like Gaussian elimination. But in contrast to Gaussian elimination, I'm going to work from the bottom up. So let's see. So I'm going to start with rows 4 and 5 to eliminate that entry in row 5, column 1. Then I'm going to move up a row, rows 3 and 4. And then, so that's zeroed out. And then I'm going to keep going, G, rows 2 and 3, rows 1 and 2. So this entry is still changed in the process of zeroing out the one below it. All right. So now I've zeroed everything below the diagonal in the first column. So then I move to the second column. So I again rotate rows 4 and 5. Now, my notation here has got me into trouble because this rotation is not the same as this one. So because the purpose of this rotation was to zero out that entry. Next one's going to zero out that entry. So I'm going to introduce another subscript here. So column 1, it's working on column 2, just so they're distinguished. So that's zeroed out. And then I'll keep going until I get right below the diagonal. So rows 3 and 4, column 2, rows 2 and 3, column 2. So then column 2 is done. And there's less to do in that column because there's fewer entries to zero. And then I have one column left. So I move to column 3. Zero out rows 4 and 5, or rotate rows 4 and 5, rotate rows 3 and 4, and that's it. So these are zeroed out, and the result is an upper triangular matrix R. Everything below the diagonal is zeroed. So now I can express Q, because all of these matrices multiplied together is Q transpose. Q transpose A is equal to R. Therefore, Q is a product of the transposes of all of these in reverse order. So it's going to be G45 column 1, G34 column 1, G23 column 1, G12 column 1, without the transposes. And then the ones for column 2, G4 column 2, G23 column 2, and then the ones for column 3, G45 column 3, G34 column 3. So that's why I was using a transposes from the beginning. So that when I was writing down how we get Q, because Q itself is not transposed, and it's a product of given rotations that are also not transposed. All right. Now I'm going to describe to you what one of these matrices looks like that's actually multiplying A. Because a given rotation is working on only 2 rows. But A is a matrix with 5 rows and 3 columns. Each of these matrices has to be 5 by 5. So for example, G45 is going to look like this. It's working on the last 2 rows. So that's where it's going to have a cosine sine pair, so that the kind of 2 by 2 rotation that you've been seeing. And then the rest of the matrix is identity, because it's not touching, it's not affecting the other 3 rows. So the upper 3 by 3 part of this rotation is identity. The real rotation is happening down here. Zeros everywhere else. Similarly, G12 would have a cosine sine block up here, the upper left 2 by 2 block, and then identity down below. I'll draw one more, like G23 would have in rows 2 and 3, rows and columns 2 and 3, a cosine sine block, a 1 up here, and a 2 by 2 identity down here. Okay. Any questions? Okay. So now I'm going to describe the, like in a pseudocode format, the algorithm for QR factorization using givens. Okay. Actually, yeah, the glare zone is just going to mess me up too much. Okay. Now, I'm going to assume a helper function here. Helper function called givens, where so the idea is this computes a cosine sine pair that zeroes out B. So we use that to get the cosine sine pairs for each one of our rotations. Okay, so I'm going to work on each column from left to right. And then within each column, well, first I'm going to set Q equal to the identity matrix. And I'm going to work on A and reduce it to R. And I'm going to accumulate all these transformations to build Q as we go. So for each column, I'm going to work on the rows starting from the bottom and working my way up all the way down to the row that is immediately below the diagonal. So first I need to figure out what Gibbons rotation am I going to use? What's my cosine sine pair? So I'll call my Gibbons helper function passing the appropriate elements of A. So I'm trying to wipe out Aij. That's my B here. So what goes here? The element directly above it. So that would be a I minus 1 column J. So I'm taking two entries, one right above the other, and I'm treating it as my 2 vector, this, and figuring out the cosine sine pair that will cause this to happen. Okay. So once I have a cosine sine pair, my matrix G will be okay. A lot of room, unfortunately. So it's going to have the identity matrix of size right, so for instance, okay, because I is going to be at least 2. So identity matrix of size I minus 2. Then my cosine sine 2 by 2 block. And then identity matrix of size m minus I. Like I've shown you over here. It's the same idea. All right. Then I can multiply the transpose of that with A. And what that does is Aij equals 0 as a result of that transformation. And then to accumulate transformations in Q, all right, I can multiply on the right by G without the transpose. So once I come to the end of this, so I'll have a m by m matrix Q such that A is equal to Q times R. So in the end, the matrix A with overriding is R. Or what I could have done, actually, this is preferable. Set R equal to A and just work on R. So that way you're not destroying A in the process. So this will 0 entry starting from the bottom, working our way up. I actually posted homework problems for this chapter. Well, we're going to spend a lot more time on this chapter. So it's not going to be due for quite a while, like over a month, because there's also spring break and all that. I will have to correct what I have for givens. I'll have to check the notes also and see if it's right in there. So I'll take care of that. Because one of the problems is to implement this in MATLAB. But one thing to keep in mind is the way I've written it here, okay, the way I have it written here, if you just go ahead and code this as is, with G being an m by m matrix, that's going to be way too inefficient. You need to take into account which rows or columns are affected. If I multiply R by this matrix G transpose, which rows are affected? So this only affects rows I minus 1 and I. So what you can do is you can overwrite rows I minus 1 and I of R by taking the appropriate linear combinations of them based on the cosine sine pair. So what's really happening is row I minus 1 is equal to, it comes from here. So C times row I minus 1 plus S times row I. And also row I is equal to minus S times row I minus 1 plus C times row I. So what you can do is you can overwrite these rows of a matrix with these. So if you code it carefully, but keep in mind, if you write it just like this row has changed. This is the original row. So be careful about that. But this way, you're not carrying out a full-blown multiplication of m by m matrices. That's just way too expensive. Similarly, this only affects columns I minus 1 and I. So you can implement that in a similar way to reduce the number of operations. Now, as far as the overall expense of this algorithm, it's a little more difficult to express because we're not dealing with a square matrix. It's not just going to be n squared or n cubed because we have m and n both to take into account. Now, you're working on n columns, and you have a varying number of elements per column to eliminate, but the number of total entries to eliminate would be on the order of m squared times n. Wait, no, that's not right. No, order m squared, because you have m, then m minus 1, m minus 2, etc. That could be bounded in terms of m squared. The number of elements that are affected by these operations could be as many as n, because you're working on a row, and these rows have n elements each. Now, the other thing, as you move from left to right, you're working on these two rows, but you're working on smaller and smaller portions of those rows. Because, for instance, suppose you're working on the second column. Everything down here in the first column is 0. So if you do this to elements in the first column, you're just manipulating zeros. So this affects rows I minus 1 and I, and also columns j to the n. So first time around, yes, it's affecting everything. But after that, less and less. Okay. But the total cost is order m squared n. Because of how many elements you have to get rid of. All right. Questions about the algorithm? Well, it might be a good idea, like when you're implementing this. Well, that's another thing for any of these assignments. If I have a problem, like write a MATLAB function to do this, test it. Like, for instance, for something for solving A equals B, make up A and B like random matrices, and try it out. Make sure it works, because even if you don't, I can. And just for fun, I can run your code, and hopefully I don't watch it crash. So do it yourself first, and save yourself heartache when you get it back. Um, okay, so even if a problem itself doesn't explicitly state that, I mean, that's the easiest way to make sure that your function is actually correct. To try it on a problem, and like if you compare it to what MATLAB would produce by using backslash for like if you're solving ax equals b, that's the easiest way to check. Um, so, because I've gotten code from classes like this, like 561 in the past, where I was like, I look at this code, it's like, oh, you didn't run this at all. So, okay. And if you're not able to get it to run or run correctly, that's when you ask me questions. And try to get you through all that. Okay. Now, the whole reason we're doing this in the first place is for solving least squares problems. So there's one thing I want to point out is that this part of the algorithm that accumulates Q is likely optional. Meaning that it may not, for your application, whatever you're doing with QR factorization, you may not necessarily need to compute Q explicitly. Now, if I go back to what I gave earlier, the how we use a QR factorization for a least squares problem. So we minimize b minus ax so solving r1x is equal to c, where r1 is just the non-zero part of R, so it's these upper n rows. So we obviously have to go through and get that. C is the upper part of Q transpose B. So we need these first n elements of Q transpose B. So you might think, oh, well in that case we must need Q to compute Q transpose B. But we don't. Here's why. Q transpose B, if you're multiplying anything by Q transpose, we already know how to do that because we multiplied Q transpose by A to get R. How do we do that? One step at a time. All the givens rotations. So it's kind of like a Gaussian elimination, like how you learned it in your first year algebra class. You're applying these row operations to A, and you're applying the same row operations to B. So implicitly, you're carrying out the Ly equals B solution. So when you're figuring out which givens rotations to apply to A, if you also apply them to B, then you're computing Q transpose B at the same time that you're computing Q transpose A. So Q is never computed explicitly. It is computed implicitly because if you keep track of all the givens rotations, like what are your cosine sine pairs and which rows, you store all that information, which is a lot less storage, then that is enough to build Q if you really need it. But as long as you're carrying out these individual rotations anyway on A to get R, you might as well carry them out on B just to get this. So you work on this vector with all your rotations. You get this modified vector. You take the first n components of it, and that goes up here. And then you carry out your back substitution, and you're done. Now, if you're solving like several least squares problems, like the same A but different B's, that's a different story. You still need to keep track of all this information. You need to, just like with Gaussian elimination, you're keeping a record of all your multipliers. That you store them in L. It's the same idea. You need to store enough information to work with Q, even if you never build all of Q as an explicit matrix. So sometimes representing things like Q implicitly with the information that's needed to build them is preferable. Because applying each one of these rotations is very cheap, especially when you're doing it on a vector. You're just twiddling two elements of that vector. Okay, so that's a key point here, is that when you're implementing QR factorization, it actually says you really need Q. An ideal way to implement this in MATLAB is like you're writing a MATLAB function that has two outputs, Q and R. And MATLAB has a variable nargout, which is how many output arguments were requested. So if a user requested two output arguments, they want both Q and R. And if they only request one, they only specify like R is equal to QR of A, then you assume that they only want R, because certainly that's the most important thing. Okay, so this is one way of computing QR factorization. And I wasn't expecting to use a whole time doing it, but again, I didn't expect to screw up givens either. It's not the most efficient. So the approach I'm going to cover on Monday, household reflections, actually can be pulled off in somewhat fewer operations. But givens is the most flexible, and the reason why is it zeroes out one element at a time. So you can do do pinpoint work. Like, for example, suppose your matrix is nearly upper triangular, like it's banded or something. There's only a few non-zero entries below the diagonal. Then givens is great because you just pick out the rotations you need to zero out only those elements, and you're done. Or what if you need to update your QR factorization? So a common task is you have to add or delete columns from your matrix A, and you already have a QR factorization of A, but now because of this insertion or deletion, you now have to update it. So givens is very effective for that, compared to the other approaches I'll show you. So on balance, givens probably is preferable, but as I said, the reason I'm teaching all three approaches is there's no clear winner among them. So they all have their uses. Okay, so I'm done. All right, so well, on Monday we'll see how you're doing with the homework. God help us all.